welcome. It's the 22nd of January, 2016, and this is episode 40 of the Unseen Podcast. Joining me tonight, from left to right on my Hangout screen, are Adam Smit.
Hello.
And Ciro Villa.
Good evening, Paul. Good evening, everyone.
And Nielsen.
Hello, everyone.
And Patrick Festa.
Hello.
Okay. Well, it's been a kind of a crazy week. Lots of interesting things have come out. I think we're going to talk mostly about the things that have come out recently and what they imply, and we're just going to let the conversation go where it will. And most of these things have to do with interesting developments in space science, astronomy, and even a little bit of SETI-related astrobiology related. Well, I'm just rambling here. Somebody stop me. Let's talk a bit. Okay, let's start with the Kardashev thing. Roughly 50 years ago, I think Nick just said 64, there was a paper that came out by a Russian fellow named Kardashev, and that was in English. I think it may have come out earlier in Russian, and which he categorized civilizations, planetary civilizations, into three categories. And a new paper just came out recently by am I pronounced this right? Serkovich?
Yeah, Milan Serkovich.
Yeah. Somebody want to give us a quick summary of what that was about?
Basically, he reviews the history and the status of Kardashev's now famous classification or scale of extraterrestrial civilizations.
Right. And he thinks it can be improved a bit, right?
Well, yeah, Kardashev's scale has been around for a long time, and it's often criticized as being somewhat simplistic. Whether that's a fair criticism or not, I'm not sure, but it's certainly scientific thought and methodology is always a work in progress. You know, we should always look to improve our classifications of anything. And basically it is just a timely review of our way of looking at or looking for extraterrestrial civilizations and how they might appear to us from across the universe.
Right. For the people that listeners are not familiar with that, let's sort of quickly review what is a Kardashev 1, 2, and 3 civilization. Anybody want to take a crack at that?
Well, it depends on whether you want to talk about how people. I've often said that the Kardashev Scale classification is a Rorschach test because people tend to read into it whatever they want to read into it. Michio Kaku is particularly notorious for making claims about it. If you read Kardashev's actual 1964 paper, it's pretty simple and pretty straightforward. He says that a type 1 civilization uses energy about the level of contemporary civilization. He was writing that in 1964 when energy use was a lot less than it is now across the planet. And a type 2 civilization is a civilization that can make complete use of the energy of its home star, and a type 3 civilization could make complete use of the energy of its home galaxy. But there are some minor equivocations and ambiguities in Kardashev's formulations that certainly could be improved. But it's become a commonplace well, there's a question of whether you want to call these things improvements or whether you want to call them other people making variations on the theme. Carl Sagan wrote a paper about Kardashev. I can't pull the name of the paper off the top of my head, but he reformulated a little bit and said that contemporary civilization was a 0.7, and that's become widely adopted within the community of people who discuss these sort of things. And one of the themes that Michio Kaku likes to hammer away on is that Type 1 civilization has bypassed or gone beyond the use of fossil fuels, and that doesn't appear anywhere in Kardashev. But if you want to say it, you can say anything you like, I guess.
Right. Now, didn't Sagan and Kardashev actually collaborate a bit?
Sagan collaborated with Shklovsky, I think.
Oh, right.
Life in the Universe. I don't think he wrote any papers or books with Kardashev, but of course they were they knew about each other's work and were influenced by it.
Right. I was just remembering that wrong. Okay. So now the interesting thing about the three different types of Kardashev civilizations is they would have completely different observables, right? I mean, that's the scientific part of it, right? You would expect with Kardashev level 1 civilizations that it might be kind of hard to observe them from a distance. Kardashev level 2, you might be able to see some waste heat from their stars, and Kardashev level 3, you might be able to see waste heat from their galaxies. In other words, the galaxies wouldn't look like you'd expect to see a completely natural galaxy to look, and Kardashev 2, the star would not look exactly like you expect a completely natural star to look. And
in the original 64 paper, Kardashev actually proposes that a couple astronomical radio sources might have artificial sources. There were some, I think they were early discovered quasars that were very powerful radio sources, what were subsequently understood to be the result of astrophysical processes. But one of his points in the paper was that it would take a civilization on the level of a K3 civilization to broadcast like a radio galaxy. I mean, it would be so bright, you'd see it on the other side of the universe, just like we can see these extremely distant radio astronomical objects by radio astronomy. And it would take a Type 2 civilization to be able to receive just about any transmission from anywhere.
Mm-hmm.
But even a Type 1 civilization could receive the transmission of a Type 3 civilization. Whether or not it could interpret it would be another question, but that's, a natural astronomical radio source, like a radio galaxy, can be seen from, like I said, across from one side of the universe to the other practically, as long as you're within the same light cone. That was the idea of a K3 civilization that would be so bright and so obvious that basically you couldn't miss it.
Right.
There was a recent study in September of 2015, which I believe we discussed it on the show last year, regarding, I think it was a Penn State University study where they pretty much say
the G-Hat study. Yeah.
Where they say that in the local universe there was no sign of detectable level 3, Type 3 civilizations, based on some of the analysis they performed on what they believe what should be the signature of a Type 3 civilization.
Right. Well, what they found is they didn't find any local galaxies that exhibited the signature of at least 88% of the galaxy being absorbed by a civilization.
Yeah.
Which did not leave me stunned and surprised.
I have to say that's to me I can't see any civilization being able to how do I oversimplify this? Use the entire galaxy as an energy. So I can't see it.
Well, I mean,
they said.
Go ahead.
They said that any such civilization must be at a significant cosmological distance. They didn't rule out such a civilization existing. They just said that there are no signs of such a civilization in the local
universe.
True.
Exactly.
And as we discussed it back then, it is a good paper. They did do good work there. They were mining the WISE data primarily, which the
or infrared signatures, which presumably would be informally, what they were looking for was a Dyson sphere, because everybody thought that a Dyson sphere would leave an infrared signature from its waste heat.
Well, they were looking for basically it didn't really have to be a Dyson sphere, just some way of trapping a high percentage of an entire galaxy's energy, and that would leave a lot of waste heat. That's pretty much unavoidable. You can't, as far as we know, there's no physical way to get rid of the waste heat except to radiate it out as infrared. It could be in different bands in the infrared, but the WISE covers a wide range of infrared, and they didn't see that. They didn't see anywhere that they saw a few galaxies that looked kind of interesting, but they didn't see any that were clearly signatures of a K3 civilization. I think that was good work. But got to ask yourself, is that a little bit too top down? I mean, would any civilization? Let's assume again that Einstein was right, that you can't transmit information faster than the speed of light. So, would any civilization have that kind of top-down organization that it would capture a whole galaxy's energy at any one time, any one instant?
Well, one of the ambiguities of the Kardashev classification is some of his formulations are in terms of the equivalent of. So it depends on how you want to read it. If you want to say a civilization that uses the equivalent of energy output by its star, it doesn't have to actually capture the energy of its star. Or if you say a civilization that uses the equivalent of the energy of an entire galaxy, then it doesn't have to actually capture, build an actual Dyson sphere around a galaxy, which is not going to be a very successful engineering project. So can a civilization harness energy at those levels? Well, that becomes a question of whether the technologies that they master and how scalable they are. We don't know that yet.
Yeah, I was thinking a similar thought that Nick just mentioned. For example, in particular, what if they have the civilization is so advanced that has found the ability to harness more exotic forms of energy? What about dark matter? Is it far-fetched to think that they might have been able to do that? I don't know. Would harnessing dark matter still leave an infrared signature?
Well, yes, it would. Well, I mean, I really don't know that, but I mean, the laws of thermodynamics say you should have waste heat. Now, could you get the waste heat into dark matter instead of photons? Well, it depends what dark matter is, right?
Dark matter follows the laws of thermodynamics, absolutely, but we don't even know what the nature of dark matter is at this stage, other than the fact that it behaves as an augmentative type of force to gravity, right? I guess.
Right. I mean, could you somehow dump the waste heat into cold dark matter? Yeah, well,
I don't know.
I don't think anybody can tell you the answer to that question, but
exactly. Well, right.
Here's another theory. Here's another theory of hidden civilizations being born: is that all that energy is dark matter is the result of waste energy from super civilizations.
That would be fascinating.
So then we'd have to explain why it happens to occur in halos around galaxies. But
that's kind of a stretch. But then again, everything we think of is that you can always invent more entities, right? That would that would explain it. But
hence Occam's razor.
When we bring in Occam's razor and say, okay, too many entities, we already have an explanation.
Well, now we're in the situation of having entities that we know are out there, but we can't explain, like dark matter and dark energy.
What is the easiest explanation of dark matter at this point? Is that an easy explanation of dark matter? Well, a simple one?
Well, I think the essential approach to dark matter is it's something fundamental to the universe. It seems to work well with cosmology. very early
That
universe.
doesn't necessarily explain what its very nature is, its fundamental nature.
Well,
don't know
the
that.
simplest.
That's true of
the
all
simplest
matter, though,
answer-
right? We don't know what the tau what the tau and the muon are about, but they're there.
Exactly.
They exist.
At least we have ways of measuring taus and muons by contemporary science, but we can't yet detect a particle that's a dark matter particle.
Right.
But the simplest answer would be that they're WIMPs, or weakly interactive massive particles. And there are several scientific experiments going on right now to try to detect if they are WIMPs and if they are related to dark matter. But that's very highly speculative at this point.
Right.
Yeah. And I think we have to wait till those experiments play out till we find out.
Well, one thing we know for sure is that there's an enormous amount of dark matter in the universe.
Yes,
An
there is.
enormous amount. That's one of the incredible things about it.
And the question is, would an extremely advanced technology be able to find a way to interact with dark matter and exploit it? I don't know. But I don't mind the speculation. We encourage speculation. But we have to admit that we simply don't know. It may be impossible to interact with, except gravitationally.
Yeah, it's essentially inert. I don't think dark matter is a very good candidate as an energy source.
Exactly. That's a great point. I was going to say something similar to what Adam just said. We slapped the definition. I mean, I don't know the exact origin of why it was called dark matter to begin with, but without knowing the nature of dark matter, I don't even know that. Why do we call it a matter? I mean, matter is something substantial, right?
Well, because
actually,
it seems to not be. It seems to be moving slowly, and
it has mass.
It has mass.
Actually, the name.
And that mass interacts with visible things like stars and galaxies. So.
Right. The original name was simply dark matter because they didn't know what else to call it. And since they couldn't see it, it simply was dark.
Right.
Which is why the confusion came about with dark energy, and they're not the same thing. They're not about the same thing. It's because the dark energy was also an energy they couldn't figure out how to measure or something to that effect. They unfortunately became the same name on the first name, but they don't have not much to do with each other.
Yeah,
I think it was
dark
first
matter,
coined by Fritz Zwicky.
Like Nick said, dark matter is in fact gravitationally interacting with the matter that we know about.
Right.
And since we couldn't see it, they simply called it dark matter, just for the namesake.
Well, I know that. I understand the name not dark. I was just referring to the word matter.
Well, it behaves just like
matter.
matter. It's attracted gravitationally. It seems to be cold. It seems that it's just not moving around at high temperatures or moving fast. It stays in an area like a galaxy cluster, as if it were matter, but it doesn't do anything that results in photons emitted. So that's why it's dark.
Right.
It's not ordinary matter. There's more of it than there is ordinary matter. We don't know what it is exactly, but I think that I have great respect for those who are trying to experimentally understand its true nature. And we may only be a little ways away from having some understanding of that, or a long way. We don't know.
I believe that the term dark matter was first coined by the astrophysicist Fritz Zwicky way back in the 1930s, when he discovered that galaxy clusters were moving at huge velocities that were hard to explain based on just the stellar masses of galaxies.
Right. But back then we didn't really know. We didn't know. Couldn't account for the masses of things like clouds of hydrogen or other dark things that are completely ordinary and understandable, right?
But he was essentially right.
Yes, he was
essentially right. It took
until the 1970s.
It took decades for people to reconcile themselves, and many different figures following Zwicky, drawing attention to the fact that things weren't quite right with the difference between observed entities and the measurable mass that seems to be acting according to gravity.
Well, we didn't know how to do the math. We didn't know how to do the arithmetic back then. The accounting was the observational evidence wasn't strong enough about. I mean, we hadn't even started radio astronomy. So things like big clouds of dust and gas out there that don't emit a lot of light or don't emit any light at all. They emit in the radio, or they have some kind of inferred signature. Those had to be accounted for. And when they were accounted for, they didn't add up to enough. And that was really, now that we have a pretty good, neutrinos. We didn't even know that there were neutrinos back then. Now we do know neutrinos exist, and we know they have a certain amount of energy. They're not enough to account for the missing mass. So now we have a much, much better idea, and we can't, the math the arithmetic just doesn't add up. We have not enough matter. So you have strange behavior of galaxy clusters. You have galaxies that rotate faster than they ought to be able to rotate without flying apart. And all that has to do with, and if you add up everything that we know doesn't emit light, you still don't have enough matter. So
a small correction, not enough baryonic matter. That's why we posit dark matter in addition to baryonic matter.
Well, yeah, I mean,
because the cold, dark, silent gas and dust that accounts for a lot of matter is still baryonic matter, and there are ways of detecting it according to conventional astrophysics. But there's no way right now, hopefully soon, to detect dark matter, other than its
effect,
influence, its effect.
The effect,
just like Neil deGrasse Tyson says of black holes, you can't see the beast, but you can see the paw print of the beast.
Yep.
Yeah.
Excuse my scientific illiteracy, Nick. What is baryonic?
Baryonic is the name that we give to matter that exemplifies gravity, the strong force, the weak force, and electromagnetism.
Well, essentially, the elements of the periodic table.
Well, a baryon is a heavy particle like a proton, right?
Ordinary matter.
Yeah.
Ordinary matter is called baryonic matter. Everything.
I appreciate that for myself and for our audience.
Everything other than anything that is baryonic is non-baryonic. It's the opposite of non-baryonic. I don't know.
Right now, so we have, and there's a lot of experimental work going on right now to try to understand dark matter. It may or may not result in a positive detection, but anyway, it's a success even if it is a negative detection. That means that is something else.
Right. If we can rule out WIMPs, that's an advance.
Yes, certainly. And the theorists will go away, scratch their heads for a while, and come back with, well, why don't you try X? And then we'll look for X, and then we'll see if that's out there.
Well, look how long it took to figure out that neutrinos exist and to characterize neutrinos. It's taken 70 years, something like that. I think that from theory to detection was probably maybe 20 years. I'd have to check on that, but it's only in the past couple of years that we've really got to grips with neutrinos.
Oh, but no, they were detecting neutrinos back in the 70s.
They were detected, but I think what Adam is implying is that we really didn't have a good handle on them or a good theory of them, whereas things have become significantly more sophisticated over the years of building neutrino detectors and analyzing.
Well, the standard model incorporated a neutrino mass, I believe, in the 80s, if I'm not mistaken.
But we didn't. What I mean is, we didn't realize that they changed flavor.
Well, that's because they had mass, and that came out of the solar neutrino experiments in the 60s and 70s, where they were finding not enough neutrinos, right? And that was a big puzzle for a long time, and the puzzle got solved by saying, well,
what if 1987A?
Now, what if neutrinos do have mass? Maybe they do change flavor as they propagate, and that solved the problem.
Yeah. Then there was the infamous new supernova 1987A, where they were theorizing about certain particular ideas of supernovas, and they thought it would be giving off neutrinos, and lo and behold, thanks to their neutrino detector that they had built some years before that, they did detect the neutrinos, and supernova 1987A became famous for that particular helpful tool.
Yes, there were two neutrino detectors, one in Japan, one somewhere else in the world, and they both detected the neutrino flux from the core collapse preceding the fireball of the supernova.
Right. Well, I mean, yeah, there were a lot of neutrinos there, and they now, I think that there's a pretty good handle on those in the standard model. Yeah. And that's something that slowly develops over the last 30 or 40 years. It's not been.
I would expect dark matter to be the same. It may take another 2-3 decades for us to really get to grips with what dark matter is, but I think eventually it will be found to be a subatomic particle that will just slot into the standard model very easily. There's no big mystery. We don't know exactly what particle it is or how big it is. But
I mean, it's a mystery until we figure out if it really does fit in the standard model, right? I mean,
yeah.
I think a lot of physicists are just saying, please don't fit in the standard model, please, because that will make my career. I'll have something new to work on.
Yeah.
They're
still looking for signs of supersymmetry at the Large Hadron Collider.
Well,
CERN, but there's no sign of it yet.
True.
And there are an awful lot of physicists must be worried about that because they've based their entire careers on looking for supersymmetry and positing that supersymmetry does exist.
But that's how it's going to be a physicist from now on. You're going to work on something, and then your great grandchildren are going to find
the solution,
true or false, and it may be false. It just takes the economic cost of doing high energy physics is going up so fast.
What happens to the kid grown up that says great grandpa was wrong?
Well, you just say, hey, grandpa, you were wrong, and and here's why. And hopefully great grandpa, if he's still or she is still a great grandma, is still able to talk to them and say, okay, cool. That's how science works. Let's move on. I saw this really moving thing that I think it was a couple of years ago, where the initial BICEP results came in that seemed to confirm inflationary theory, and a very young scientist, probably in his 20s, goes to Andre Lin's house, knocks on the door and say, we've got the results you were looking for. Inflation is confirmed.
That's right.
And he was so moved and so appreciative. And now he's probably heartbroken, but because no, it's not exactly confirmed. There's other possible explanation for the same data. More work has to be done. That's life in the big city, and I in my heart I feel that Andre Lin was right. He got it right the first time, but he's going to have to. Hopefully, he'll live long enough to see the confirmation.
I think that these are exciting times, though. It's amazing to me to even think that it hasn't even been 100 years since. This is to me really amazing. There hasn't even been 100 years since we found out that there's more other galaxies other than the Milky Way in our universe. was 1923, right? I believe when it was found by Hubble. Was it Hubble found?
Yeah, Hubble. And his silent partner Humason discovered that the distance scale to the Andromeda Galaxy was much, much larger than anybody previously had been willing
to.
Using Cepheid variables as the standard candle.
Yeah.
That was the breakthrough.
It took just a lot of hard work observing night after night in an observatory just above downtown Los Angeles, just north, which would now be impossible because of the light pollution. But
was it Mount Wilson?
Mount Wilson, yes.
Mount Wilson. Yeah.
The Hooker telescope.
It was the big telescope there that made it possible.
It was the best telescope in the world at the time, and Mount Wilson was, at that point, not a high light pollution area. And Hubble, actually, it was Humason. It was Humason who was up there night after night doing the observing, taking these plates.
The most significant thing about that was that he discovered that Andromeda is moving away from us. Or not Andromeda, the other galaxies.
Well, that was later.
Are redshifted.
That was later. First, they found out that, at that time, the size of the universe was a big controversy. Nobody knew how big it was. But they kind of figured,
there was a big debate, wasn't there?
Yeah, Andromeda is one of the closer nebulae. They didn't know what it was. They just called it a nebula, or a big thing out there.
A spiral nebula.
And they had no idea it was that far away, and it was the closest one, right? So immediately the whole scale just blew up.
Yeah,
and the human view of the universe just.
Well, we take for granted now that we have, we're part of a universe that contains billions and billions of galaxies. And my point is that it was not even 100 years ago that we did not. And so, expanding on that concept, I believe that even things that might be looking pretty hard nowadays, like dark matter, as far as being able to find out what they're made of, it might not be that far-fetched. Like Adam was saying, that it may be maybe even 30 years, right? That we might be able to find. Of course, we cannot predict the future, but it's not far-fetched to think that we might be able to find the true nature of it with technology.
I have a unique perspective on that.
Yeah.
Ciro says not even 100 years now. I'm 56. My father, who's still alive, is going to be 91.
Yeah.
In February. And he was born in 1925 when TV had not yet been invented. And the radio was just starting to catch hold.
Exactly. That's my point.
And I have a unique perspective because, when I went into high school, that's when they sent up the Voyagers, and we were talking about first seeing the Neptune and stuff like that. And, I have this perspective. I see these things change. I see the ideas change. When I was in high school, for example, let's just say they were arguing over whether or not it was possible for a planetary system to be orbiting a multiple star system. Now, not only is it possible, but it's confirmed. It's things like that. These progression of things over in my lifetime, and then viewing trying to view through my father's eyes, seeing that before my time was him, and he's still alive, and I can still see that he doesn't have any idea that some of the stuff that I realize. You put it into perspective that way. So it's almost like predicting, but at the same time, you really can't.
We are lucky, aren't we, to live in this golden age of astronomy. In my lifetime, we've discovered what quasars are. We've discovered that black holes exist. We've discovered that the universe is expanding at an accelerated rate. We've discovered all this stuff, so much stuff about the universe.
But I also add that we've answered one of the big questions that troubled the 20th century, which was whether the universe would expand forever or expand and then collapse. And now the money is on expanding forever.
True. I think the collapse scenario seemed to be off the table for the moment, anyway.
Well, up until
I've never understood why people worry about that. Why should we worry?
Well, there's, on the one hand, there's the possibility of worrying about it or not worrying about it, but on the other hand, there's just the scientific fascination of answering the question.
Yeah, I get that.
Well,
Yeah.
I think with immortality being right behind the corner, in about 20 or 30 years, we might have to worry about it.
Yeah, just probably right after the day I die, our mortality will become will become commonplace. Yeah, well, I think that I remember as a student in the 1970s being told about the Big Crunch, how the universe is going to go up to a certain point and then come back down, and many trillions of years later it'll and Douglas Adams' restaurant at the end of the universe was about the Big Crunch, right? The end of the universe when it all comes back together into a singularity.
Pulsating universe.
Yeah. Well, or just, that's all of existence. It comes out, it
cycle.
goes back in, and that's it. And you're done, baby, except that we have time travel now, so we can be dead for tax purposes and that sort of thing.
I think at one time they were calling it the Big Bounce.
The Big Bounce or the Big Crunch.
Big Bounce. Big Bounce. Yeah, the big, and then you got the Big Rip.
Now we have worried about the Big Rip, or the end of everything, where in deep time where everything ends and then there's a quantum fluctuation and something starts over again. Nobody, really nobody knows if that.
They're still being
True.
considered. They're still being considered. I mean, the theory. I think that the main one. I think Nick was saying that is the heat death. Right. That's probably the more widely accepted one. But I think that there's a lot of theorists that are still considering the other ones. I forgot which in particular, but I know that some schools at the Perimeter Institute.
Yeah, there are a lot of theories out there, but the older question that you find in the books of how much matter is there in the universe, how it's going to shape the structure and fate of the universe, has been answered in favor of heat death. But that's making a lot of assumptions, but a lot of assumptions that are very well based in contemporary science. Whereas if you have to take something like the ekpyrotic scenario, you get the creation of the universe not from a Big Bang, but from the collision of brains in string theory, and that requires a significantly different conceptual infrastructure that is not yet mainstream, although there are a lot of people working on it.
Right, and let's face it, that's as sophisticated as that is, that's still very highly speculative, and we really don't know what we're talking about. I'm glad that some of our smartest people are thinking about it, but let's face it, we don't really know. And as Adam pointed out, there's really not much point in worrying about it this age in time.
I remember in the 90s. I'm sure you guys probably remember that there was not an article that was not talking about string theory. There was a big fad, quote unquote, at the time was string theory. Now it's almost completely fallen out of favor, as far as
there's still people working on it, but
it was a big thing. It was
the
highly
big
publicized.
Exactly. Every other article was about string theory.
Well, it was the hot thing then, and there was good reasons for it, because string theory did seem to unify everything we know about physics. But the problem was they never came up with anything that could they weren't doing a lot of calculations, and they desperately wanted to. It wasn't because they didn't want to or they didn't think calculations were important. They did. They've struggled with
calculations were very
how
difficult.
they can get there.
Well, we don't have the energy levels yet in our experimental apparatus, but you can't yet talk about it in the past tense. Yes, a theory like string theory is going to come into popularity and out of popularity several times before we reach the energy levels where we can actually test these things.
Right. Well, nobody's come up with anything that really works at the Planck scale, which is the extremely small, extremely high energy world, and that's the scale at which the extremely early universe existed, and that's really the only thing that you can test. So the only way we can hopefully test string theory currently is by looking way back into the early universe, and people have held out hope that looking at very long wavelength gravity waves might give us some insight into that. But we're talking about not about the kind of things we see in the cosmic background radiation, but earlier than that. And
I wouldn't say
setbacks on the gravity wave detection.
Well, you have to be able to see gravity waves, but you also have to be able to see, the gravity waves they're hoping to find at LIGO are too short a wavelength to really tell us much about that very early universe. They need LIGO is great, but it's going to hopefully open a window in astrophysics we haven't had before. But it's really LISA that will hopefully give us some insight into the early universe, and that LISA's a few years away, maybe even further. So.
Yeah, the test. The LISA Pathfinder's just got to the Sun-Earth L1 point today, I believe.
Wow.
Yes, I believe that's correct.
Is that right? They just got there? I didn't know that.
Yeah, just today.
It takes a while to get out there. It's about a million miles away.
1.5 million kilometers.
Even once we start getting real data from gravity waves, assuming they're confirmed, which they haven't yet been experimentally confirmed, it's still going to be several decades before we are able to improve and refine gravity wave observations where they get down to the point, like Paul says, of talking about the Planck scale. And we get to, like I said, we're still several generations of technology away from having instruments large enough or sensitive enough or refined enough to test some of the predictions that would come out of string theory if we had technology to pursue that science. But we can't even build the experimental apparatus today in order to test those theories. But that doesn't mean that it won't ever happen.
No, I think we're going to have to look at astrophysical events to any hope of finding even the slightest confirmation of string theory, and they're going to have to do the calculations. So, we're a ways off, and my sense of it is, and this is just my gut feel, is they're onto something, but they're going to have to give us some numbers that we can check out, and that could be generations away. All the low-hanging fruit has been picked, in terms of the Standard Model is an enormous achievement, but it leaves a lot of questions unanswered. The next question:
we need a theory of quantum gravity.
Well, that's what string theory gives you, but maybe there's another theory that's better. Who knows?
We need some kind of unification of general relativity and quantum theory, though whether it'll take the form that conventional quantum gravity theories that have been proposed is another question entirely.
All the quantum gravity theories so far have not really reached the level of theory. They've been more they're theories in the mathematical sense, but not theories in the physics sense. So, we're a ways away. Even guys like Feynman gave up on quantum gravity that after enormous frustration. They hit all these mathematical infinities that they can't get rid of. And these are the same extremely clever people who got rid of the mathematical infinities in quantum electrodynamics. So
they get rid of them by renormalization, and
which is completely valid, by the way. Now we understand that, but
well, if you believe it's understood that well, but I really think that eventually the theorists are going to have to tangle with the mathematics of higher infinities, and instead of rejecting them and renormalizing, embrace them and take it farther. But that's just my personal speculation.
I think that they've got a pretty good handle on it, and it's kind of subtle, but But it's also quite rigorous. So I think that, the standard model works well, but it leaves a lot of unanswered questions. Why are the coupling constants what they are? Why do we have, and how do we? And it doesn't bring in gravity at all. So now a lot of physicists will tell you, well, gravity, that's the poor cousin living out in the trailer park. We don't even bother with gravity. But over large scale, gravity rules the universe. So,
yeah.
Now, can we get
understood?
I was wondering if I could change the subject.
Yeah. Can we move on to a couple of recent things I'd like to talk about before we close out? One of his, what is it? Plan 9? Is that what it's called? Plan 9?
Plan 9. No.
That's what I wanted to talk about.
Sorry, I didn't hear you there.
That's what I was wondering if I could change the subject, because that's what I wanted to ask about. So apparently,
Pluto Part 2.
Apparently, under some new calculations, sort of the same way they found Neptune way back when, by doing calculations of the perturbations and things like this, they decided that there should be a planet there doing these perturbations. Apparently, now there's some new calculations that have shown that the inclination to the plane of the Kuiper belt objects could only be if there's this large object, something like the size.
Well, it wasn't the inclination so much; it was the arguments of perigee, which essentially what that means is that the long axis of the orbits are kind of clustered together, rather statistically. They're not all lined up perfectly, but
okay,
they cluster over on the same side.
Well, in any case, in other words, there has to be, or there should be, this large object, something like 10 times the mass of the Earth, something like a Neptune-sized object that has this very elliptical orbit that is shepherding these objects in that way.
Yeah. Now, I should point out, one of the people involved in this research is Mike Brown, right?
Yep.
The Pluto killer.
Pluto killer.
And Konstantin Batty again.
That's his Twitter alias, isn't it? His Twitter alias.
It's his redemption.
Yeah, that's
his Pluto killer. Is his Twitter
Pluto.
alias.
He's the proud. He wrote a book about that.
Really?
Something about how he killed Pluto or something.
So who's more guilty, him or Dr. Tyson?
I don't know. But he and Alan Stern are going to have a duel of swords, I think, to settle this issue.
But anyway, so I'm like intrigued over this. In fact, while this podcast was starting, I noticed that the news guy David Pakman show actually on my news feed shows breaking: our solar system has a new ninth planet.
No.
I mean, in other words, while we were actually starting this podcast, that came up on my news feed. So.
Oh well.
Okay, well, this is something that the mainstream media tends to get wrong. Some of them got it right, but they said ninth planet discovered or something, or 10th planet discovered. No, it has not been discovered. It has been hypothesized to explain the clustering in the arguments of perigee of the other Kuiper belt objects that are known.
The scattered disk population of Kuiper belt objects.
Yeah.
Yeah. Objects like Sedna.
It is an interesting and probably real anomaly in the statistics, which
it is. they argued that it's the chances of the alignment of these scattered disk objects is something like 0.007% chance of them being randomly aligned like that. So looking at it like that, that's fairly strong evidence that something is shepherding these Kuiper belt objects in their orbit.
I think you'll see a lot of different analyses coming out over the next few months that will have different results in different probabilities. But yeah, I mean, it does seem like so far, based upon the discoveries we have to date, which is not a large number, that something is perturbing these objects in a way that is systematic and could be a large. And what they did is they put in a certain mass and size, and they tried to find something that was the most probable, and they modeled it. But nobody has put in a telescope at this thing and found it. Okay.
Right. But they're also suggesting that it even may be what's tossing comets our way every now and again.
Could be.
I was listening to Pamela Gay, who's an observational astronomer, on the Weekly Space Hangout earlier, and she was saying that it is possible that astronomers have seen this object, but because they weren't looking for it, they didn't know, they didn't see it as a planet.
Right. Well, I can assure you right now that there's a bunch of astronomers data mining.
Thank you, Ciro.
Observational data and old photographic plates looking for some evidence of it.
Thank you, Ciro. That's exactly the graphic I was looking for.
What we really need is something like the Large Synoptic Survey Telescope that's in the process of being built now. And we need a telescope with the right cadence to see such an object moving.
Right.
If it does exist, this planet would be on something like a 10,000 year orbit around the solar system. It moves extremely slowly.
Right.
So
well, I mean, I think there's actually Mike Brown put out an article, I guess an interview today, where he said probably, even any decent telescope could find this object if it knew where to look.
Right.
Exactly.
We just don't know where to look.
You don't need the James Webb Space Telescope to find it. You can find it with it.
I don't know if anybody's seen it, but Ciro's got a very cool graphic up.
Yeah, I'm watching Ciro's graphic right now.
This is an animation of the purported, trajectory, if you want, an orbit of the so-called Planet 9.
Yeah, right. It has.
I don't think
zero audio content, but
there's no audio.
Right.
I don't think it's going to be that easy to see. It could be extreme. It's going to be very, very small on the night sky.
Well, according to Mike Brown, it shouldn't be
very, very cold.
It shouldn't be obscenely faint. Is what he said.
Yeah.
That if you had a good telescope and you knew where to look, you could find it. You're not going to see it with the binoculars. You're not going to see it with the naked eye, but you'll see it.
Seeing it move, though, is the trick to identifying it. We need to see it move.
Right. That's because there are hundreds of thousands of background stars of that magnitude, and you're not going to be able to tell them apart unless you see it move.
Now it's the inclination. It's at least the orbital inclination or approximate orbital inclination. Is that predictable? Is that known?
Yeah.
So
they predict it.
So in a way, that eliminates a lot of areas of the sky, right? Is that a fair statement to say that?
Yeah, it could be a pretty wide part of it, and they don't really know what phase it's in. But when it gets close to the sun, which may be a long time from now, you should be able to see it.
But my point is, if we can predict a plane, or at least a number of a range, right, an inclination range, so we have we can eliminate a large portion of the sphere, right, so to speak. So that should at least narrow. I know it's still not.
Yeah, you can narrow it down. I don't think you can exactly nail a small portion of the sky. I mean, telescopes tend to view very, very tiny fields of view, and that's why what they're good at.
Right.
This new paper predicts that this object should be in roughly the same plane as the distant Kuiper Belt objects that have been found recently, like Sedna, VP 2013.
Yeah, well, anything that big had to form.
They predict that its perihelion would be 180 degrees away from them. So you'd need to look in the opposite direction in the night sky.
Yeah.
Which is a bit strange, but
well, they all go around the sun, but the anything that large could not have formed out that far. It would have had to form much closer to the sun, so it got kicked out by
or been captured.
Well, not captured, but
it could have been.
It had to be kicked out. Well,
it could have been captured.
We
don't know.
Well, there's even some ideas that we may be sharing the outer solar system, meaning way beyond even the Oort cloud, the heliosphere, sort of sharing it with Alpha Centauri, because the distance from the radial distance between the sun and the very outmost influence of the gravitational sun is so far away that it may actually overlap our nearest neighbor heliosphere. So there may be, according to some ideas, I don't know how great of an idea it is, but they're actually considering the idea that they actually may be sharing, like swapping outer solar system objects, minor objects.
Well, the most likely scenario. Yeah, go ahead, Adam.
I don't know about sharing, but I understand what you mean. It is possible for Kuiper Belt objects, in particular Oort cloud objects, to be swapped by other star systems. Could easily have comets that are kicked out of their system and end up in ours. There are comets that could have originated in the solar system that get flung out into neighboring star systems. But I don't think we share, the gravitational influence of Alpha Centauri doesn't have that much of an effect on objects in our solar system.
That's correct. It does.
Well, the idea was
basically zero.
The idea I saw was that the outer edges of our solar system could be as far as a light year, and if the other star, Alpha Centauri, specifically Alpha Centauri, because that's the closest one, is also a light year, maybe even a light year and a half.
But it's
outer
over 4 light years away.
Left.
Yeah, they would still not intersect. If that was the case, they would still not be intersecting.
Yeah, but the thing is, this hypothesized Plan 9 is so large that it could not have formed out there where it is now. It had to be formed much closer to a host star, where you'd have enough density of gas and other
inside
material.
the frost line. You mean?
Yeah. Well, I don't know if it's inside the frost line, but it had to be much closer than it is now, and it would have been kicked out probably by interactions with other planets to a much higher orbit. The whole solar system in its early days evolved a lot from what we see it now, and we think of the solar system as unchangeable, but it actually changed a great deal in its early life. Just as we all do when we're young, we change a lot, then we sort of settle into a personality. This thing, if it's out there, and it may be, it's not a crazy idea, probably got kicked out there a long time ago, billions of years ago, by interactions with other planets. But they're talking about something slightly smaller than Neptune, bigger than Earth, bigger but smaller than Saturn. So
about 10 Earth masses.
Yeah, 10 Earth masses, which is like a super Earth, but and by the way, such a thing would almost certainly be undetectable in other solar systems as an exoplanet, because it just doesn't transit very often, even if it transits, which is unlikely. So we would, if it's out there, we should be able to find it with enough careful searching. And if it is, that's really cool, but it doesn't, what am I trying to say?
It doesn't come anywhere near us.
Right. It's not, okay. You guys who think this is the Sumerian Nibiru, go back to sleep.
There was an astronomy. There was an astronomy teacher that said it best. I think it was yesterday regarding Planet 9. She said, I am pretty confident that I will be spending at least the next year explaining my students and the public that no, we haven't discovered Planet 9. Because that's what the populace now thinks, is that yes, there is a Planet 9. Definitely there's a Planet 9. That's not the case. There's not definitely a Planet 9 out there.
Right. No. At the same time, there's the blowback from the Nibiru idiots out there.
Yeah,
well, that's another story.
I mean, certainly if there's real data that shows, like I think there is, that shows there's a possible semi-large body out there that's orbiting in a very elliptical orbit. Certainly, I'm going to follow that, but that has nothing to do with my thinking of the stupidity of
well, also, I would like to say that Alan Stern, who is a serious person, will tell you that no, it's more like Planet 11 or Planet 12 or whatever,
right?
Because he would consider Pluto and Sedna and others to be real planets. So, but you know what? I don't want to get into that debate at all. I think that's kind of.
Well, Alan Stern just got awarded the Carl Sagan Prize.
Yeah, that's true, and he deserved it. But I think that this debate about what's a planet and what's not is kind of the modern version of angels dancing on the head of a pin.
Yeah, well, that's just it. I'm not coming from there. I don't care what they call it. As far as I'm concerned, they reclassified it. That's fine with me. But I'm interested in the actual, data. I'm interested in the actual. Hey, do we actually have another planet out there, or what? That's what I'm interested in. I don't care what you call it.
Planet X.
It's a celestial body.
Just don't call it Nibiru.
Yeah, I know.
I think that's quite a good idea, Paul. Why don't we reclaim the name? If they do find it, I'd like them to call it Nibiru, just to reclaim that name.
Well, you have a point there, Adam. It might turn off the woo-woo if we.
What's the other one? Planet X? Was Planet X origination from the same as Nibiru? Was like another name for Nibiru? Or was a different story altogether?
Planet X was originally Pluto.
Well, it was actually Neptune, wasn't it? I thought it was Neptune.
Planet X was Pluto? I didn't know that.
Well, there were planets that were unknown that...
I thought it was another imaginary, quote-unquote, imaginary planet.
Or maybe it was just any planet that they haven't labeled yet, and they called the Planet X. So
I thought that there was another one.
Neptune, it was X. When it was Pluto, it was X.
I thought it was a planet that the public thought it existed, but it didn't exist. It was a similar story as that of Nibiru.
There's Vulcan.
Oh, Vulcan, between the sun and...
Vulcan is a classic, right? The planet on exactly the other side of the sun from Earth.
Yeah.
Right, yeah.
Which is kind of a silly idea if you think about it, but...
Astronomers seriously thought that planet existed around, 100 years ago. They searched for it, never found it.
Well, you can't see it
because
if it's
not there.
On the other side. Yeah. Well, we know now it's not there, yes.
Yeah. Well, stereo is out there now looking at both sides of the sun, so.
That's true.
Yeah,
Stereo could see it if it was there, but it's not.
But that was before they understood what the fluctuations were caused by. I think it was before the Einstein relativity theory. They were not sure exactly. They thought the only explanation for the fluctuations was that there was another body between the Sun and Mercury. That's what Vulcan came about. Then finally they understood that that was not the case. There was a physical explanation for that wobble, I guess.
Before we say goodnight, I want to just briefly talk about Tabby's star. I've done a lot of work on trying to understand that lately, as have a lot of other people. About 8 days ago, I interviewed Bradley Schaefer, who is the astronomer who found that the star, based upon historical data going back to 1890, that the star appears to be dimming. Now, Bradley Schaefer is a very serious astronomer. He's not some kook. He's got serious credentials. He's contributed to Nobel Prize winning work. He's an expert on looking at old photographic plates and trying to determine the magnitudes of stars. And what he did is he went back. There's something called DASH, which is a project to digitize the old Harvard plate collection. Now, the Harvard plate collection is a collection of old astro photographs from going back to 1890 or even before that. These are taken from a large number of telescopes over a long time. There are thousands and thousands and thousands of these plates at Harvard. DASH took on the project of digitizing the plates and determining the magnitudes of stars from the plates, which is a very impressive feat of modern computer science as well as astronomy. And what Bradley Schaefer did was he took those data, plus he went back to the plate library himself. He'd been there before. It wasn't his first trip there. He's done photometric research at Harvard many times. And he looked at Tabby's star. Now, we should, just for a little context, Tabby's star is the one that has been found to have had some very highly anomalous transits. That is, something is passing in front of the star that is much larger than any planet could be, but doesn't exhibit the photometric properties of another star. More research has been done showing that there's no close companions of the star. And I'll have links in the show notes to all this information. But I interviewed Bradley Schaefer, and you can listen to that interview on the Wow Signal podcast last week. And he essentially found that the star was dimming slowly over the historical data that we have available to us. And he also found this both in the digitized data and his own visual measurements from the old plates himself. And this is it. And he's very careful, and he understands the nuances of photometry and looking at photographic plates. And what he found was a magnitude of about 0.165 per century dimming. Now, that's a logarithmic scale. 0.165 is actually a lot of dimming. It turns out to be something like 20%. 20% is enormous. All the models say and all the data say that no star on the main sequence, which is most stars, should be dimming by that amount in a century. No way, no how.
Well, stars don't dim at all.
I've placed a diagram from Schaefer's paper itself on the screen.
Yes. Now, what you have to remember, what he did was he had over 1,200 magnitudes measured from DASH, and he took over 100 himself personally. And what he found was, now there's an interesting little dip there in 1900 and 1905. He's not convinced those are statistically meaningful. They may just be noise, but there's no systematic error here. Everything is very carefully done. So what you see there is real. Now, those are binned. What he did is he took every 5 years, he took a mean of the measurements that he had, and he binned them together for those 5 years. So it makes a lot more sense. The other little marks you see on the screen there are his check stars. He took some nearby stars that had about the same color, and he also did those measurements to verify they are not trending down. Because that's how you do science. You check and you try to find proof that you're wrong, right? You try to find evidence that you're not just making some systematic error, or that the photographic plates just don't have there's not some kind of trend in the emulsions. And what he found was that, you can see that in that plot, and I'll have a link to this paper in the show notes, that there's a trend. Now, if you consider that dip in 1900 and 1905 to be real, you get an even stronger trend. If you consider it to be random, then you get the trend that he got. We don't know what that dip in the early part of the 20th century is. Now, this is only 100 years or so of data. It's not, in astronomical terms, that's nothing. But you should not see this kind of dimming in any kind of main sequence star over that kind of time scale. And so this is a big anomaly. Now, does that justify jumping to conclusions? No. Does it stimulate a lot of speculation? Yes. It's really interesting. Now, this is in addition to the very short period dips of a few days that we see in Tabby star in the Kepler data. So, what's going on at Tabby star? Nobody knows. There's no good naturalistic model that explains it. And there's a lack of infrared excess, which means that it doesn't appear to be a Dyson sphere being built. However, I want to point out that Marshall Eubanks on Facebook had been talking to me, and he's and other people, and he's pointed out that the millimeter wave data is at least consistent with a very cold absorber at a considerable distance from the star. So we're not done.
That's what I would suggest.
Millimeter wave data is looking at, even longer than long wave infrared. It's looking down in almost that nether region between radio and infrared, where there does appear to be some excess, but it's not certain by any stretch of the imagination. It's really upper bound, so it's entirely possible it's not real. So stay tuned.
I was always wondering if it wasn't just either a large body at a very wide orbit, hundreds of years worth of orbit, just starting to move in front of it, or perhaps a number of bodies. For example, instead of an accretion disk, maybe it's a solar system forming, and there's this large amount of stuff in a large wide area that's starting to move in front. It's not formed as a planet, or it's not formed as any object yet, but it's large enough to, a lot of stuff there to cause this light interference.
Yeah, well, that's the first thing they thought of, Patrick. And so what do? You go look for, there's a picture of Bradley Schaefer up on the screen, with a very old telescope. But what that's the first thing they thought of. They thought, well, maybe this star is younger than we thought, and maybe it has a disk of forming around it, and it's somehow clumping in interesting ways. So they went and looked at the WISE data, and they would expect to see an infrared excess, and they didn't see it. And so I think that's pretty well ruled out.
Is the star old, or do they know the age of the star?
They don't know the exact age, but it does appear to be a main sequence star, which means it's been, it's more than. It's a mature star, but it may not be an old star.
Is it maybe a destruction of a planet? Krypton.
Well, they look for that, but you would see a big infrared excess if that was the case.
And you'd see a regular orbit pattern as well. You'd still see these objects regularly orbiting, around the star.
Yeah, but we're talking like if the orbit is several hundred years, and we're just seeing it within.
Well, you don't get accretion disk at several 100-year periods. They're much tighter in.
I mean, if it was an object or a clump of objects, and if it was orbiting the star in hundreds of years, and just happens to be passing in front of us now, it would take 100 years for it to complete.
But it's been passing in front of us for hundreds of years. That's the thing.
Right. That's right. That's why I suggested a large clump of objects. Well,
what kind of objects would those be?
Ordinary stuff that's trying to make itself into a planet. That's not in a
that's not that far out. That's the problem. We think we understand how accretion disks, not accretion disks, but how planetary disks form. Protoplanetary disks, and they only take a few million years to form, and they are much closer in than that. And so basically there are no good theories right now.
Do we know so much about stellar evolution that we can rule out a main sequence star that does change in its brightness?
I think so. Yeah, I think we do.
Well, what about the faint young sun problem? Well,
we know that young stars tend to have go through an evolution, but this is a completely ordinary main sequence star. Well, no, in terms of its spectrum and its temperature. I mean, the thing is, if you have this big ball of gas at a certain temperature, it's not going to be faint. It's going to be what it is. It's an F-class star, which means it's brighter and hotter and larger than our sun, but not a lot. It's a bit bigger than the sun. It's formed. It's not in the early stages of its formation. It's done with that. And so if there were still a protoplanetary disk forming around the star, we would see that in infrared. We don't see it.
It's fair to say that this star is going to be the most closely scrutinized star in the sky over the next decade.
I think that's fair to say, yeah.
So we will know within a few years whether or not it is an average, ordinary F-type main sequence star or not.
I'm still with Nick.
Well, we do know that already. I mean, we know that from its spectrum, its radio velocities.
Sure. I'm with Nick with the idea that there may be something out there that we don't know anything about. And it may look like an ordinary star to us, and suddenly one day somebody's going to say, you know what, this is not so ordinary after all. Or it's going to be this clump of matter or something like I said. But Nick is more qualified to speak about it than I am. I'm going to go with him.
I'm going to go with Bradley Schaefer, who teaches astronomy for a living, and I agree with him that there's no easy, obvious explanation for this star. Now, he was saying we just maybe haven't applied enough imagination. Maybe there is something that we haven't thought of. But it's something really unusual. there is certainly no other known star that has behaved like this. You can go back, and now people are doing this now. You can go back and look at the old data, and there's a lot of data, and a lot of it's on Dash, and try to find other stars that behave like this. I think you're going to find very few, if any, maybe zero, in terms of this slow dimming over.
Oh, isn't that right in the Kepler field?
It was in the Kepler field. Kepler's no longer looking in that area.
Yeah.
Yes, it was a Kepler star. Yes. But
if it weren't for were it not for the citizen scientists on the Planet Hunters project, we would never have known about this.
Correct. Yes.
I was on that project. I didn't get much out of it, though.
You didn't look at the right one. They saw these weird dips that the algorithm missed.
It all helps, Patrick. Whether you found the planet or not, all your efforts help.
Yeah, a negative result is a result. Adam's right. The citizen science people found these dips, and Tabitha Boyagi and her team followed up on them, and they, everyone should read up on that if they really want to know what's going on. And then Bradley Schaefer said, "Hey, that's interesting. Let me go see if I can find the historical data about this star." And when he did, he found, and he's an expert on looking at old photographic plates. And
he deserves a tremendous amount of kudos for what he's done.
Yeah, and he's he's probably as well qualified to do this as anyone else on the planet. And he went and did it. And
it's a great example of intergenerational science too. To think that you have essentially a long-term science project that's been in the making for 120 years or more.
Right. Yeah. I mean, and I agree with that. And if you go back to the old science work that they did back then, even back to the 19th century, the astronomers in those days knew that they weren't going to be able to answer every question, but they knew that taking the data carefully and doing the best job they could was going to contribute in the long term. Astronomers still use the Bonner-Durchmusterung, which is an 1855 star catalog.
Yeah.
Which you can still get.
An extraordinary validation of the Dash project itself. The idea of archiving the data from the old Harvard photographic plate.
Yeah, I'm told that it's this big room full of cabinets containing envelopes, and inside each envelope is an 8x10 plate, photographic plate. And on that photographic plate are a lot of dots. And
what a treasure trove.
It is. And there's all kinds of information in there that, there are supernovas in there. There's all kinds of things that nobody's found yet. And it's just waiting to be found. So that's probably our next big citizen science project is data mining Dash. But we don't know. The Tabby star is extremely interesting. Nobody knows what's causing that dimming.
Why are they calling it Tabby?
Because Tabitha Boyajian, whose nickname is Tabby, led the science team that followed up on the Kepler observations.
Oh, okay.
She's with Yale, I believe.
It was an extremely interesting object when Tabby Boyagi and her colleagues wrote their paper. I mean, now that Bradley Schaefer's found so much more out about this star, it's just become an extraordinary mystery. There's nothing ever like this that we've come across before in the galaxy. Nothing at all. I think it's absolutely fascinating.
Right. And I would point people who want to get into the more speculative area, I would say go to Centauri Dreams and follow the thread there. I'll have a link to that as well in the show notes.
There's also the G-Hat paper about what an alien megastructure might look like.
Right. And
I'm not a big fan of the megastructure ideas.
Well, you can't rule it out.
Why is that,
I'm not
Patrick?
Suggesting that
it's just one of those, I guess the Occam's razor thing, it's one of those things that are on the far less possible.
Okay, well, okay. I'm not going to launch into my Occam's razor abuse sermon, but no.
I don't know. I just don't see it. In my mindset, I just don't. Right away, people want to jump on the alien civilization thing. I'm all for finding alien civilizations, but this just doesn't.
Well, it's not Occam's razor, though, right? It's just that let's rule out all the natural explanations first, right?
Exactly. What do you do?
Yeah, precisely. Let's not jump on aliens until.
What do you do?
But aliens are natural, right? Aliens are part of. If we know that technological civilizations exist, right?
Yeah, I mean,
we are
one, right? We just don't know how rare they are.
Right.
Hence, that's why it's legitimate to invoke Occam's razor, because we have no evidence of any others. So we ought to be very sparing in that hypothesis.
We're not inventing a new entity. We're not
inventing a new entity, but we're questioning how many of them there are.
Right.
Since we have no evidence of any except our own, we are justified in being very sparing of the use of that hypothesis.
Well, right. Let's use all the entities we know about that are out there, right? Well, we've exhausted those to this point. Maybe there's some new ones that we'll come up with. I'm not saying let's jump to the alien conclusion. I'm saying let's not rule it out a priori.
No, we're not ruling it out a priori. We're putting it on the distant edge of possibility.
Well, I don't even need to do that. You just have to say, look, let's look at all the data and see where it leads us. Right.
But if we're going to discuss alien megastructures, I'd like to mention that somebody wrote a post on Tumblr, and I was waiting for somebody to say it. One of the obvious explanations would be it's a structure under construction, and that is why we would see changes in the light of the star over time.
Right, and you have to find the IR excess that fits the data, which so far we haven't.
I mean, it makes for absolutely wonderful science fiction. But it's, we need to figure out, like Nick said, well, we're not going to forget about that idea. We're going to find out some natural things that we don't know about yet.
I would sooner posit a variable brightness main sequence star than I would posit a alien megastructure.
Well, we know these stars aren't variable to that extent over those time scales.
Do we?
So
do we know for sure?
Yeah, we do know that. That's very well understood.
Well, I don't think that we understand that much about stellar evolution that we can rule it out.
No, I disagree. I think stellar evolution is better understood than that. And I mean, we have a huge sample space. We've been studying stars for 200 years, and we have a very good idea of how main sequence stars evolve. And no, they don't do this. So you've got to come up with a new physical mechanism.
Billion stars, there might be one out there that doesn't fit the mold.
Well, there might be, but you've got to come up with a mechanism for how that can happen.
And we might be lucky enough to see that star.
Well, maybe, but again, it would be a massive upset of some very successful models. I mean,
that doesn't negate the models. It just
it does. It takes. We have models that tell us, models based on a lot of data, by the way, that stars like this do not dim on those timescales. So
we just don't know what happened to it. Anything could have happened. Anything
we don't know, but right, we don't know. That's
something could have catastrophic could have happened. We don't know.
well, you got to figure out what that catastrophic thing could be. A lot of people have tried to come up with something and have not succeeded.
Right, but I guess Nick probably agrees with, or I agree with him. So therefore, I'm assuming that he's agreeing with me that we can't rule out the possibility of a rogue main sequence star that does something that we've never seen it do before.
Yes, that's exactly what I'm saying.
Well, yeah, but I mean, where is the physical explanation?
Well, we don't have a physical explanation yet. We have the phenomenon that we observed, and now it's the time for the theoreticians to step up to the plate and say, well, what could happen inside the core of a star that's otherwise a main sequence star that could produce that kind of anomaly? And I'm obviously not qualified to do that, but I don't think it's certainly outside. The interiors of stars are turbulent, and lots of stuff goes on, and there certainly is room for.
Yeah, but they've been thinking about that for generations, and they haven't got any mechanism that can dim a star.
Well, they've been thinking about stars for generations, and they just decided to come up with this brown dwarf thing only a short time ago.
Well, no, that's not new.
It's not old either.
But the thing is, F-class stars are very mainstream. They've been around for a long time. My point is that if there's a physical mechanism, it's something pretty exotic. Nobody's thought of it.
No, I agree with that. If there's a physical mechanism, and I'm not, I guess the alternative is a metaphysical mechanism. If there's a physical mechanism, it's something pretty exotic. Yeah.
Exotic.
Well, the alternative would be something external to the star, which frankly seems more likely to me that is, either natural or I think that the probability that's inherent to the star itself is pretty low. It's something external to the star that's causing it to dim. And we don't know what that is. And maybe it's something we just haven't had enough imagination to come up with yet. But the problem is of the Dyson sphere, which is a very simple idea, really. Just capture some of the starlight. But it might be simple enough to be real. You'd expect to see an IRXS that we haven't seen. So it's not straightforwardly a Dyson sphere. So we need an even better idea if you want to posit an artificial cause for this.
I know there have been people analysing the dimming mathematically to try and look for signals in the dimming. I don't think anyone's successfully managed to decipher a signal yet.
Hidden signal.
It hasn't stopped them trying.
Contact.
I didn't do it. It wasn't me.
You have to look at 3 dimensions. No, well, I mean,
an Encyclopedia Galactica.
Right. Well, I mean, the thing is, that this whatever happened would happen almost 1,500 years ago. So why would they be trying to signal us? They wouldn't. They'd be signaling somebody else, right? And we're just catching a glimpse of it.
The European Gaia spacecraft should give us a much better handle on exactly how far away it is. I think their first data release is in this summer.
Yeah,
around June, July.
We know it's roughly 1,500 light years away.
Yeah, but it would be nice to have a more exact distance measure to help characterize the star.
But the reality is, I mean, if we're seeing a signal now, then they saw us 3,000 years ago.
Yeah, I tell you what it is. 3,000 years ago, the planet is dying, and they sent out a huge fleet that is coming towards us for many hundreds of years, thousands of years, and it is now just approaching us. The entire fleet is blocking out the starlight, and we're just noticing.
No, they're going to be eaten by a small dog. Thanks to a horrible miscalculation of scale.
That's a great idea.
I told you it makes for great science fiction.
I only read funny science fiction, which narrows it down quite a bit. No, that's a problem with the whole idea of SETI. There is that they are seeing. They would, if we were getting a signal now, they would have. That's from a civilization that would have seen us 3,000 years ago, when we had no mastery of electromagnetism at all. So that would have been no reason to think that there was a technological civilization here. So why would they could tell, perhaps if they were very sophisticated astronomers, that this was a planet that had life on it, but that's all they could tell. So
yeah, well, that's the idea. That's the idea of the colonization thing. Like they found the Earth too, or they found their planet too, and they wanted to come here and check it out. And by the time they get here, we had advanced.
Well, I for one welcome our new masters from Tabby Star.
I'll be among the resistance, thank you.
I'll be your new slave lord.
Be the new overlord.
No, they're hurt. Don't worry.
I'll be the one packing the AK-47.
I just want to know what's in it for me.
Don't worry, they're here to serve man.
Yeah,
that's what they all say. That's what they all say. They've all got reptilian skins under their human faces. We know that.
Oh yeah, that's a certainty.
So a Tabian invasion is around the corner.
Well, if it is, you think there's much chance we could do anything about it?
Would you like to pull your skin jacks off now, pal?
We would send our F-18s up there to, or our power, and give them viruses from our power books. Anyway, guys, we're getting kind of close to the end here. Maybe we should wrap up and give our recommendations. So I'm going to go around and ask each of you to give your final thoughts, and also give us a recommendation for, it could be anything. Just what do you think our listeners might enjoy watching, listening to, clicking on, buying, whatever. So we'll start with Adam, who needs to go to bed.
I'd like to recommend that people go outside an hour before dawn, if they're able to, and look east into the sky. And if you do that, and you've got a good, clear line of sight to the sky, you should be able to see all 5 naked eye planets in the sky right now. You'll see Mercury near the horizon. Then above that, you'll see Venus, which will be the brightest planet. Above that, you'll see Mars, Saturn, and Jupiter at the top. All 5 naked eye planets. There you go. Go and see them.
Yeah, that's a good one, Adam. Any other thoughts on what we've talked about tonight? Okay. Move on to Ciro.
Yes, pleasure to be on the show again, obviously. And, so much stuff out there. It's really impossible to mention just a few of them. Well, I'm going to just go ahead and mention a sci-fi show that I kind of appreciate, which is called The Expanse on the Sci-Fi Channel. And it's been recommended by a lot of people, a lot of hard science fans, for its accuracy. And it takes place, part of it takes place on Sirius, believe it or not, dwarf planet Sirius. But I'm not going to reveal the entire plot, obviously. But it's a great show. I really enjoyed it. Recommended. That's pretty much it. Other than that, again, been a pleasure to be on the show, and hopefully be able to do this again soon.
Yeah, okay. And let's see, who's next? I guess Nick Nielsen.
I'm going to depart from my usual habits and recommendation and recommend music today. There's a heavy metal band by the name of Disturbed that has recorded a cover of Simon and Garfunkel's The Sound of Silence. And the video is cheesy, but I think the cover is quite good. So that's my recommendation today. So thanks for having me on the show again, Paul.
A heavy metal version of Sound of Silence. Okay.
Yes.
I'm going to have to check that out just out of curiosity. Okay, Patrick.
Yeah, I'm going to have to check that out too. But in any case, first I want to thank you for pulling me in here on the last minute notice, because I certainly didn't give any week's notice or anything like that I wanted, was interested. So it's great to be here again, and we had a great conversation. Going on the subject matter that we've been basically talking about all night, I'm going to recommend an old sci-fi book, Isaac Asimov, Nightfall. It's about a civilization very similar to our own, except that they have 6 suns. And it's somewhat religious, or it's actually anti-religious, but it's somewhat religious. That is, every 2,049 years, apparently, there's this time when only one of the suns is visible above one of the hemisphere's horizons. And at the same time, there is this very elliptical orbiting planet that they didn't know about, eclipsing that star. And it pulls them into a nighttime. These people, obviously with 6 stars in their system, are not used to having nighttime, and they're afraid of it. It actually causes them mental illness. It actually causes them to go kind of crazy. So every 249 years, there's these fires. So there's this religious fanaticals that say that the earth will burn and all that stuff. And it turns out to be, I'm not going to tell you the whole plot, but I recommend it. It's Isaac Asimov. It's called Nightfall.
Isaac Asimov, Nightfall. And is that a book or a short story?
It's a book. I've been listening to it on audiobook. I have it
okay.
on the CD player.
Yeah. I'm going to go with music again tonight because I was listening to this again recently. And it's just magical. Now, I want you, if you're not into this sort of thing, I want you to forget everything you know about music and just listen to it anyway. The name of the album is Hilary Hahn Plays Bach. This is a teenage girl playing the partitas for solo violin by Bach. It is a stunning, magical performance by an extremely talented artist. And she's now one of the top concert violinists in the world. She's in her 30s now, but that was a moment that is just irreplaceable. And you can get the CD for about $9, and you will never regret it. And you will play it many, many times. This is just, her musicianship is flawless, and her passion for this music is just obvious. And so that's Hilary Hahn Plays Bach. The composer was Johann Sebastian Bach, and whose music is a treasure that you can mine your whole life again and again. So that's it for episode 40 of the Unseen Podcast. I'd like to thank my panelists. See, who do I have here tonight? Just a bunch of guys. We have Adam Smit.
It's been a pleasure.
Go to bed, Adam. I would like to point out that it's very nearly 5 a.m. at where Adam is. Ciro Villa.
Thank you, Paul. CiroVilla.com. If people are interested in checking me out a little bit more on Google+, CiroVilla.com will point directly to my Google+ page.
Okay. Nick Nielsen.
Thanks again for having me on, and thanks to the Unseen Podcast listeners.
Okay. And Patrick Festa.
Thank you again for having me on. It's been a pleasure. It's been a while, actually, and thank you again for pulling me in so quickly.
And now we have everything you want to know about this podcast at unseenpodcast.com. This is a spin-off of the Wow Signal podcast, which is wowsignalpodcast.com. Pretty much that's all you need to know. Just go there. The music has been by DJ Spooky. And we will see you next week, episode 41. We still don't know what the topic will be. But I think that I know what episode 42 is going to be about. Because of the number of the episode, it'll probably be about simulated universes and or simulated planets, as the case may be. Now, our real Douglas Adams episode is going to be closer to Towel Day in May. But why not talk about simulated universes at 42? 41, still wide open. If you would like to participate in the Unseen Podcast, this is an open participation podcast. Just send me an email at unseenpodcast@gmail.com. I'll tell you how you can get on the panel. If you have any comments, questions, criticisms, cliches, conundrums, please go to unseenpodcast.com, comment on this episode. This is episode 40. Or you can come to our Google Plus community. We have a Google Plus listeners community. We also have a listeners subreddit on reddit.com. So you have ample opportunities to let us know what you think about this podcast, about its subject matter, about its panelists, about its recommendations, everything you want to talk about. So let's hear from you. So again, this has been episode 40. It's the 22nd of January, 2016. David Bowie, R.I.P. Good night.
Good night.